Power like an ultralight beam. This is 467 unique substrings in a wraparound string. Not my best. Okay, so we define the string base to be the infinite, wraparound string of A, B, C, D, E, F, G, H, I, J, K, so base will look like this. Z, A, B, D, so basically it's just an infinite wraparound string. So when you get to the end of the string, you go all the way back to the beginning, right? So every letter has a letter before it. The letter before A is then Z, right? Because it's a wraparound string, meaning that you go A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, and Z, and all the way back. All right, so what comes before A? Z. What comes before Z? Y. What comes before Y? X, W. So every letter has a letter that comes before it. Just note that the letter that comes before A is Z. That's the only thing that really makes this infinite wraparound string different than, the normal just set of all 26 letters in the alphabet. Okay, so you're given a string S, return the number of unique non-empty substrings of S that are present in base. Okay. Now, 10 to the 5. So since we're looking at a constraint of 10 to the 5, our solution will likely need to be somewhere around n or n log n. N squared would probably be too long, right? N squared would produce 10 to the 5 times 10 to the 5, 10 to the 10. That'll likely, in almost all cases, give you a time limit exceeded error. So let's try to think about a solution that, is at most n log n, or, ideally n. So with that said, let's look at an example. So when S equals just A, there's only one substring A. Kind of lame, doesn't really provide you with a lot of information. If S equals CAC, well, we have the substring C, which is in this infinite length string. We have the substring A, which is in this infinite length string. And we have the substring C that's in this infinite length string. But the answer is 2 because there's 2 unique substrings in the system, right? There's a C, and it's found in here. There's an A that's found in here. There's another C, but we don't count that twice. We just count the number of unique substrings that we're looking for. Okay, ZAB is a little bit more interesting, right? Because when we look at ZAB, well, Z itself is a solution, right? Z itself is a solution. A itself is a solution, and B itself is a solution. But also, A and B is in this infinite length string, right? Because this infinite length string is sorted in terms of it's each letter consecutively. So AB is a solution, and so is ZA, and so is ZAB, right? Because we're dealing with this kind of loop back system. So A comes right after Z, right? Z is before A, and so on and so forth. So we have 1, 2, 3, 4, 5, 6 total solutions just from these 3 letters. Now, this problem type is similar or should be familiar to you if you've done other dynamic programming problems, which is what led me to the intuition needed for the solution. The only caveat between this problem and a whole other set of problems is that we have this idea of the substring having to be unique. And that kind of throws a wrench in this whole solution approach. So I guess maybe what we should do first is just try to recount or think about what the solution would be if we didn't have to think about unique non-empty substrings. Let's just find the total number of substrings that are within this, what do they call this? Infinite wraparound string of the alphabet, okay? And the way that you do that using dynamic programming when you think of a substring is, well, how many substrings can I get at each letter? That's essentially what you're trying to solve. You're trying to find the number of substrings you can get at each letter and think about how long the substring is associated with that letter, okay? So the idea is, let's not use any of the examples. Let's create our own custom example because I feel like these examples are kind of poor. And that's something that, you need to consider, kind of a tangent, side tangent. When you do these kind of problems, you need to consider the fact that sometimes the examples are not sufficient and they don't really encapsulate edge cases and nature of the problem and how you should approach different situations, right? And these are kind of 3 lackluster, less than ideal, insufficient examples. So let's make our own example and we'll call it ZABXBC. Okay. Now let's think about finding the total number of substrings in this system, meaning the total number of substrings in this system that are substrings of that infinite wraparound string. Okay. Now, the way that you do that using dynamic programming is this idea of finding the maximum substrings at each letter. Okay. Now, what you essentially do is you consider each of the individual characters or letters as vertices. And you can create a substring when? Well, we can't create a substring from X to B because this would never exist in the initial string, right? Because the initial string is the alphabet in order. So we know there's an edge between characters if the starting end of the edge and the terminal end of the edge, of the arrow, the edge, are next to each other in terms of the substring, right? So Z comes before A, so there's a connection between Z and A. A comes before B, so there's a connection between A and B. B does not come before X, so there's no connection in the spot. X does not come before B, so there's no connection in the spot. And B comes before C, so there's a connection in this spot. So then all you really need to do to find all the substrings is find the longest substring at each character, right? So we'll call that L. Okay, L is the longest substring. Now what's the longest substring ending at the Z? Well, the length is 1, and it's corresponding to Z alone. Now, since there's a link between Z and A, that means that I can add in the A to all the substrings ending here. So that means that there's a length 2 substring, and that corresponds to ZA. And then when I get to here, well, I can attach to A, and A has length 2, so I can add 1 to that to make it 3, and that corresponds to whatever A substring is, adding myself to it, and I get ZAB. Now when we get to X, well, X doesn't have a previous connection, so I have to restart the longest substring as 1, and I can set it equal to X. I get to B. B doesn't have a connection to X, so I have to set it again as 1, right? Because I can't add myself to the previous thing because I don't connect to the previous thing. I don't connect to the previous thing because it isn't the previous letter in the alphabet, so we wouldn't connect with the substring, and I just get B. And then C connects to B, so I can connect myself to B's longest substring to get 2, so I add myself to it, and then I become BC. Now, these are all the longest substrings at each index, but you'll note that from this Z, right, I get a Z substring. And from ZA, well, I can get ZA, or I can get just A alone. From ZAB, I could get ZAB, or AB, or B alone. From X, I just get X. From B, I just get B. From BC, I get BC, and I get just C alone. So in total, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total substrings, right? Because the idea is as well, the longest substring I have up to this point, that's the longest one. But there's also one shorter, right? The longest one I get is ZAB. But that means if I get ZAB, I also get AB and B, right? I get all the characters together that create ZAB. So that means I get ZAB, AB, and B, right? With BC, the longest I get ending at this C is BC. But in order to build BC, I need C alone as well, so I also get C. So the total is just the sum of all of these, right? Because if the longest one is 2, I get 2 resulting substrings ending at this letter. If the longest one ending at this letter is 3, then I get 3 total. If it's 1, then 1. So if I just sum up these values, I get the longest substring ending at that letter, right? So the recurrence relationship is the longest substring ending at an index is 1. Forgot how to do this. It's 1 if the string at I minus 1 isn't 1 less. I don't know how to say this. If S of I minus 1, I'm just going to put it as a number, plus 1 not equal S of I. And I'm talking about the order here, right? I'm saying the order, so we'll call it O. So if the order of this character doesn't equal the order of the character that I'm looking at, if they do equal, then I can add myself to the previous index. If they are equal to each other, right? So if the one right before me, if the character before me isn't the character that comes right before me in the alphabet, I have to set it to 1, like the example with X, right? I have to set, that's unfortunate what I did here. So I have to set X to 1 because the character before it doesn't come one letter before it in terms of its order in the alphabet, right? But versus B, I can set it equal to 3 because I can set it to one more than the character that comes right before it, since the character right before it, in terms of its order, comes 1 before it in the alphabet, right? So that's the kind of recurrence relationship here. I set it equal to the previous thing plus 1 if the previous thing comes right before it. Otherwise, I have to set it to 1. Maybe I should have swapped the way that I did this a little bit, but hopefully that makes sense. But the problem is right, so where this becomes problematic is, well, that would give you the total number of substrings that are in the wraparound infinite string. But we don't want the total number of substrings. We want the total number of unique strings. And you'll notice here that we have repeating terms here. Right? So if we returned this solution using this recurrence relationship, this dynamic programming approach, it wouldn't give us the right answer because it would return 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 solutions. But our answer is supposed to only be 9, right? Because there's only 9, 2, 3, 4, 5, 6, 7, 8. There's only 9 unique substrings. So that's where it gets kind of complicated, right? And that's why it's important to have a strong fundamental understanding, because I got all the way to this point. I got to this point just using my previous knowledge of dynamic programming. But from here, now I need to practice, some new intuition because I'm in untraveled, charted, whatever waters, right? I'm in a position where I'm unfamiliar with what to do next. But if I had no previous exposure to these kind of problems, I'd be completely lost. I wouldn't even get to this point. But it's important to take a problem and try to break it up into parts, break it up into a component that you already understand, and then think how you can build on top of that to get to the final answer. So from here, how do we capture the idea of a unique string? Well, I'm trying to think about the best way to describe this. It makes sense, but it's hard to elaborate on in detail. The idea essentially is, right, if we're looking for a unique string, right, what is the issue? I guess we'll start here. What is the issue in this problem? Well, the issue is that we already get ZAB here. So since we get ZAB here, we're going to get ZA and AB and B. So this B becomes irrelevant, right? Because if the longest substring I get ending in B is 3, if I get a longest substring, for example, if this problem was a little bit different, so let's adjust this problem to think about maybe the, so when we go through this, if we start it up again, right, we get Z, and then we get ZA, and then we get ZAB, and then we get X alone. Now, imagine there was an A in this position. So I'm going to insert in an additional node just so that we can see something in practice, right? So this is one of those problems where it might be helpful to try to derive a few examples, right? This is definitely one of those problems where the examples lead you to the solution. Okay, so if we have just A here, where here I would get A is 1, and I'd get B is 2, and I'd get C is 3, right? Now, these will provide our additional strings, right? Because this will provide Z, this will provide ZA and A, this will provide ZAB, AB, and B. This will provide X. I don't know why I typed things twice. A, B, and B. This will provide X. This will provide A alone. This will provide A, B, and B. And this will provide A, B, C, B, C, and C. So where are the issues in this problem? Well, we notice that we're counting what over and over again? Well, we overcount A, right? We overcount AB and we overcount B here. So why does that happen? Well, if I have something ending in A, right, whatever its length is, I'm going to get A and the letter before it and the letter before it, right? There's only a substring ending at A, right? That's ZA or YZA or XYZA or WXYZA, right? There's no other such substring. So when I get the substring ending at A, it can only provide me with those finite substrings, right? If the substring ending at A is linked 2, it's going to provide ZA and A. So if I encounter another substring ending at A and it's shorter, then I'm already getting that information from the previous thing. Meaning, when I'm here and I find a substring ending at A that's linked 2, if I see another A and the substring's linked 1, I'm going to say, well, I already captured that A in something that's longer. Right? I already have a longer solution that provides me with an A. So I don't need your answer. Right? And then when I get to B, I'm going to get to B and I'm going to say, okay, B, I can provide a substring with link 2 at B. Right? So it can provide me with A, B, and B. But I'll notice that, no, I've already encountered a B that has link 3. So since I've already encountered a B that has link 3, I'm already getting I'm already getting B, I'm already getting AB, and I'm already getting ZAB. So if you're linked 2, all you can provide me with is B and AB, but I've already got that covered. So what I'm basically saying is, instead of having to build a set where we try to add every single possible substring, we could just keep track of the longest substring ending at a character, and that'll determine all the substrings that you could create. And if you get that same character again, if the length is not as long, that means that we've already had all those digits covered, right? Since the length of this is 2, it can only provide me with A, B, and B, and it's always the same, right? So if I have something that ends in B that's linked 3, I already have A, B, and B covered, so I can disregard these. Right? So instead what we need to do is we need to add in an additional constraint. When we do this, and we say like the longest ending at a letter, right? So here the longest ending at Z is 1. Now at this case, the longest ending at Z and A is 1, 2. And then in this case, the longest ending at Z, A, and B is 1, 2, and 3. I'm just saying the longest thing ending at Z is 1. The longest thing ending at A is 2. The longest thing ending at B is 3. The longest thing ending at X is 1. Now, at this case, we're counting an A again. But since this A is 1 and our longest A is 2, the idea is essentially, well, sure, I can get an A substring here, but I already found something of link 2 ending in A, and that already captures the A itself. So I don't need to use this A. I just continue down the path. And then I get this B of link 2, and I say, well, you know, I know you can give me an additional 2, but those additional 2 are already captured in this B that I found of link 3. So you'll provide me with A, B, and B, but I have a longer link substring of link 3 ending in B, so I already get A, B, and B, and Z just by counting that. You're not giving me any additional information, right? So it stays the same here. And then when I look at this C, right, this C will give me 3. And I haven't even seen C yet, so that's obviously the right answer. So we kind of need two things here, right? We need to keep track of the longest substring we've seen so far, but we also need to keep track of the longest substring ending at that unique letter to determine every time we see a letter if the new thing can provide more or not, right? Since I already have ZAB, AB, and B captured here, if the system ending at this index isn't longer, then it's not going to provide me with more substrings. It's actually going to provide me with less. So I don't need to account for it, right? So I just keep track of the longest and the longest at ending, and then at the end I just sum up these values, right? Because these values will say, well, the longest thing I got ending at Z, so all the unique substrings I have ending at Z, I have 1. All the unique substrings ending at A, I have 2. All the unique substrings ending at B, I have 3. All the unique substrings ending at X, I have 1. All the unique substrings ending at C, I have 3. So the idea is, well, first we're going to use, I guess in summary, how we're going to do this is we're going to use this idea of finding the longest substring ending at an index, right? We find the longest substring ending at an index to determine all the substrings in the system, and then we use the longest substring ending at a letter to determine the number of unique substrings in the system. And that's the general idea of this problem. So you have this idea to find the longest substring ending at an index, and then you say, well, for each thing, the longest substring ending at this letter index, this should be index, right? The longest substring ending at this index equals the maximum of whatever it was before and whatever the longest substring is ending at this index. So we kind of have this weird idea of we want to find the longest substrings ending at an index and the longest substrings ending at a letter to find the unique one. So to find all the longest to find all the substrings, we look at the longest substrings at each index. To find all the unique substrings, we find all the substrings ending at a letter. Right? What's the longest substring ending at this letter? That'll compute all of these substrings ending at this letter. Right? What's the longest substring ending at some subsequent letter, and so on and so forth. So this is the relationship we're going to use to solve this problem. Okay. So we'll do the longest at the index. We'll just call it L. I don't really like the terminology I used before, but it's kind of too late now, right? Now you'll notice that for L, we can just do it as a running sum, right? Because these values are only based on the value that it is currently, so I don't need to create a whole array for L. I do for LE though, right? So longest at ending at an index, we'll just call it default dict 0, lambda 0. And then the longest is 1, and then we'll say S equals 1, right? Because we'll start the operation from this point forward because there's nothing to compare this one to before. So the longest at the beginning is always 1, right? And then the first letter is always 1, right? But there's nothing to compare it to before, so you can't make a decision about like what the longest is ending at this index, right? Because the longest thing at the first index is just itself, and the length is 1. Okay, so we'll look at the range I, we'll call it index, in range 1 to the length of S. And then we'll play this game, right? So now we just do this recurrence relationship. So the longest equals 1 if they're not, next to each other in the alphabet. Otherwise, the longest is the previous thing plus 1. So we'll say the longest equals 1 plus what the longest was before if it's the case that the order of the string at I offset from the string of so maybe I should do it a little bit easier. So we'll just create this. It's going to make 26 operations, but it's fine. A, B, C, D, E, F, G, H, I, J, K, L, M, O, P, Q, R, S, T, U, V, W, X, Y, Z, A. So times int S of index minus 1 to index plus 1 in S. Right, so if it's in S, then one of them comes before the other one, right? If you have ZA, it'd be ZA here, AB here, right? All the letters are in this case. So this will give you 26 operations. So it's going to slow down our code a little bit, but it'll make it a little bit more readable. Other way, you'd have to look at the order of everything, right? But this is basically saying if they're together in this string, then one comes before the other one, right? And then you could just say, okay, well, now then the longest substring ending at this index is, well, whatever we thought it might have been before, or whatever else providing us with here. And at the end, we just return the longest substring at each of the indexes. So sum longest substring values. Longest substring. Why'd I call it ls? What's wrong with me? Longest ending is, I think, my initial idea, and then I changed my mind. Because I'm a fool! All right, cool. So let's actually make this a little bit shorter. Just so people can yell at me in comments and say, your code is so unreadable. It's not about being readable. All right, so what's the run and space complexity of this? So let's say n is the length of s. Okay. Now it's kind of a tricky kind of problem. All right. Because, well, for time is pretty straightforward because we just look at each index. So we look at all n indexes and then we make a comparison, right? And we set the longest ending based on, you know, the two previous things. I mean, based on what the longest was before. So this is definitely constant. You might argue that this is n time, right? But what I'm trying to do is find if two letters exist in S. But S is just this 27 character string. Regardless of the input n, right? If n is 1,000,000 or n is 10 or n is 100,000, we're always just trying to find if two letters are in S. So this is a constant operation with respect to the input, right? So even though, like, you may say this is inefficient because I'm like looking for a string and a substring, this substring is a fixed size regardless of the input. So since it's a fixed size regardless of the input, it's constant with respect to the input. So this is a constant operation and this is a constant operations. So for all n indices, we do constant operations and then we return the sum of LE values. Well, that's never going to be greater than n, and in a second I'll show you that that's also constant. So in terms of time, it is O of n. All right, we look at all n indices to make a decision. What about space? So space is where it gets a little bit more complicated, right? Because we create this default dict, and then we populate this default dict, right, with values. So doesn't that mean there's n possible values? Well, no, there's n indices, but the values at each indice can only be lowercase letters. So there's only 26 lowercase letters that this could possibly be, right? We're only going to set 26 keys within LE because there's only 26 possible things that the value could be at each index. So even though we're like setting values of LE for each index, we're only setting one of the 26 letters in terms of the keys that we're setting values for. So that means that there's really only O of 1 space that we're using here. Okay, guys, that's it for today. Hopefully this problem made a little bit of sense. I know it's a little strange because you're doing like this weird combination of finding the longest substring at an index, but to find the longest substring ending on a letter, you look at each letter individually. All right, peace out.